So we start with the last part of PN junction, and for the diode we have seen that current voltage characteristics under reverse bias does show two components, one which is constant with reverse bias, the other which varies with reverse bias, which we call as the generation current. However, if we keep increasing with reverse bias, as we say on this side, somewhere around one value which we call breakdown, VBS we can say, the current starts shooting again. At that time the current may reach very large value, typically it can go to amps, and if the device is not heat protected it may even burn. So what happens, why such characteristics is seen, that certain value of V breakdown we see large currents. There are three mechanisms which I said. One of course is called avalanche, word suggests something, avalanche breakdown. The other possibility is Zener breakdown. And third, and the most important among them, is punch through. So either of the mechanism can lead to large currents at a bias. Typically avalanche breakdown can be as low as say 10 volt, can be as high as maybe 5000 volts. Zener of course is normally less than 3 volt, and punch through can be as low as 10 volt and can even exceed 5000 volt. So depends on your requirement of the device, one can find out where do you want your breakdown to be available for you. In power devices we need large reverse breakdowns, typically of the order of maybe at least 2000 to 5000 volts, whereas in the case of normal electronic devices 100 volt breakdowns are more than sufficient. Okay. 100 itself is large value, 30 volts is even good enough. In transistors for example, the base collector junction at best can stand 30 volts. Okay. And therefore in most devices using PNP or NPN junctions, one finds that the breakdowns are typically low. Okay. Whereas power devices can have breakdowns of the order of thousands. Okay. So let's look at the mechanism. The first one, the word suggests there is something called avalanche. So if I bias a diode under reverse bias, and if I start reverse biasing this device, initially the intrinsic W was this much, W0 we call it zero bias, and the reverse, the depletion width starts enhancing towards PN region as I exceed, as I start increasing the reverse bias. Since this increase of W, you can see from here now, essentially what is going to happen is it will enhance the electric fields. Initially the built-in field was say 0.6, 0.8 volts, now it can become V0 plus VR by 2W, 2V by W, and we figure out that the electric field starts rising. So let's say this is my boundary, x is equal to 0 and x is equal to W, and this is the depletion layer, and we assume now that under reverse bias electrons will like to go here and holes will like to go here. Under reverse bias holes will look for polarity which is same as electric field, electrons will try to move opposite to the direction of electric field, and because of that this may be possible transport. So as soon as an electron enters from say P region into N region or thermally generated in the depletion region, In that case, an electron here with large electric field present to it will acquire sufficient energy. If you have a larger electric field, force acting on that is Q times electric field. Larger the electric field, larger is the force, that means larger kinetic energy picks up. Now if this electron becomes energetic enough, and if you see your silicon bonding, a covalent bonding, and if the electron is coming with high energy, it may actually hit a bond and may break this bond, okay. And if it breaks a bond, what it will do is, it will create one electron hole pair. If it creates one electron hole pairs, now since the electric field is large enough, before they recombine, they can get separated. This is an important issue. If the electric field is large, they will be separated faster. If the electric field is smaller, they may recombine before they get separated. Since the fields are larger in reverse bias, they will get separated. Now these holes which are coming here, let's say plus minus again. Now this will try to go here, but when it tries to go this side, it will also acquire electric field, it will see electric field and will acquire energy, and it may also do electron hole pairs. Similarly, this electron, when it moves further, may acquire enough energy and can keep breaking the bonds. This is like a cascade effect. So what is happening is 1 creates 2, 2 creates 4, 4 creates 8, geometric kind of. Let's say probability of ionization, this word is called ionization. So if the probability of ionization is P, then if N is the number of electrons entering here and in, and N is the this, N out by N in, will be, if P is the probability of ionization, P electrons will become P square will be P cube, P4, P5, and it keep on enhancing unless, by the time when finally electrons and holes are picked up. Since the number of electrons, holes coming out of the depletion region are very large, at the end of the terminals, large electron hole current can be seen. Larger the current, the IV characteristics will start shooting larger and larger currents at similar biases. Now this fact that one can, what is the sum of this series, can anyone say? So if the probability of ionization is close to 1, N out by N in can be as much as infinite. Is that correct? So larger the ionization probability, larger is possibility that N out will be very, very large compared to N ins. By similar logic, I can say hole entering from the N side going towards will also show you large probability, and therefore when they come out at the P side, they will have larger number than what they initiated with. Is that clear? This means larger hole electron currents. Oh yeah, the problem is something like this. This electron being energetic means basically what is bond? Bond is the attraction between the two atoms. As soon as I hit an electron, that means this energy I am giving to the bonding electrons. Now these bonding electrons right now are bound to the atom because of the Coulombic force. If the energy is larger, the atom will actually move away, okay, vibrate faster. So the bonds will be broken. As the bonds break, electron hole pairs, one electron will jump out of it, creating hole there, and then hole will further accelerate, each will create one electron. It's something like this. From valence band, I am putting an energy to go to the conduction band. As soon as I create an electron in the conduction band, I create a hole down. What is bound state? Bound state means valence band. From the valence band, an electron going to conduction band is essentially creating a EHP. Each EHP then can create more EHPs, and EHPs can create more and more and lead to what we call avalanche of carriers, and therefore the breakdown mechanism was called avalanche breakdown. Details you can read more in the other book. This is the theory which leads to this. Typically this factor is called M, we call avalanche multiplication factor, and if M tends to infinity, we say large current will start flowing. Yes. Okay, now this electron itself is available to you. It also will accelerate. That is how N out by N in I am taking. Whatever is initially I introduced, they will get multiplied now. That itself will move. Some may recombine as well because their recombination probability is not 0. But most of them before they recombine will be separated because of the electric field available. So this essentially reason why at certain large value of voltages one finds larger reverse bias, suddenly heavy current starts. So what is the limit of voltage up to which you can operate a device? The breakdown voltage. Anytime diode you want to be switched off in the reverse bias and it will turn on heavily. So I don't want on state for the diode under reverse bias. So I must protect my device by every time going below. In electrical engineering, the word use up to which you can use this value to the maximum available is called what? Derating. Okay. So you should always derate the numbers. Let's say its avalanche breakdown is 1000 volts. So you are not allowed to go beyond 700 volts. Okay, 70% derating is the safety margin for all electrical engineers. Okay. So don't say that, oh, you said it 1000. No, 1000 is the reason is this is all probability issues. Okay. So one doesn't want to say exact doping is how much every device, every place. So one says derated values are always 70% of specified, maximum specified. But it doesn't mean you can never operate at 800, 900 or 1000. It does allow you, but not, then you must first check some way that is breakdown where, and then if you check every device, yes, you can go to the maximum. Okay. Otherwise, always derated values are used. Okay, so this is the first mechanism which we can do, and it can be shown. Of course, as I say, I will not like to give you more details. Where alpha is called ionization rate with which ionization takes place. Okay. Alpha n is ionization rate for electrons, alpha p is ionization rate for, ionization means breaking a bond. So ionization rate for holes. Right now we assume electron and holes have same ionization rate, alpha. So this one can see from here, if this alpha integral in the depletion region tends to 1, then this value m will tend to infinite. Okay. So whenever ionization rates are functions of electric fields, the doping, the trap densities, so many other cases. So real life situation may not be so trivial, but just assume in our case that ionization rates in this value does reach closer to 1, m tends to infinite, and therefore avalanche breakdown can occur. To do analysis, which I did, I'll give the final value for this, which is most important. Okay, what is the voltage if EVR is the electric field at which this occurs? So what is the voltage sustained? 2V by W is EVR. For a abrupt junction or step junction, this is a good formula. Okay. So I can find from here what is the value of breakdown voltage, and I have evaluated this. You can evaluate yourself. Ks epsilon 0 upon 2Q, and this EVR is many times called critical field at which breakdown occurs. E square upon 1 upon NB to the power minus 1. NB means what? What is NB is called? Why B? Normally in step junctions, one of the side will be heavier doped than the other. So in a P plus N junction, N is lightly doped region is called the base. because that will be form a base in a transistor, so we use the same word. The heavier dope region will have lesser depletion, but larger depletion will go into the lightly doped region. That region is called base. So in P plus N junction, NB may be how much? NDs. In the case of N plus P junction, it can be NAs. So a common word is used as NB. NB stands for base concentration, which can be either acceptors or donors, depends on whether it is P plus N junction or N plus P junction. So one can find, and just typical this electric field, which or ND, is of the order of 10 to power 4 volt per centimeter. Typical electric field at which ionization can take place. Remember why this field is required? Because electron must acquire sufficient energy to knock the bond. This is the field at which one may say knocking of bonds are possible. So EC should be at least 10 to the power 4, 4 into 10 to the power 4 in some materials, 6 into 10 to the power 4 in some other materials. Depends on the material property. This critical field will be the order of 10 to the power 4 volts per centimeter. At this electric field, depends on the doping, one may get your breakdown values. Is that clear? So these numbers are decided by what? What will these numbers will be decided by? The base concentration I choose will decide my breakdown, avalanche breakdown value. Is that correct? Whatever N or NA or ND I use for the base, that may decide the value of breakdown. Just check it, I think it is correct. The way I had written is correct, because this -1 may become M for other cases. So it is why that was kept like this. Okay. Just look at this. I just derived it. Maybe I made mistake, but just check it. Now, this is the first mechanism of breakdown. Can you think the third one directly without even going to the second one? Just look at the situation, please. If this is very, very heavily doped, and this is very lightly doped, minus means lighter doping, plus means heavier, and plus means heavy. So where will be the maximum depletion will come? N side. As soon as I start reverse biasing, the depletion will only go into the N side. Not that it will not go into P side, but the width is extremely small in the ratio of dopings of N and P. Since you are heavily P++, much of the doping depletion will only see in the 99% may go into the N side. Okay. Since you are depleting, it may occur at certain voltage, whole of this N region gets depleted. If your diode lengths are say 10 micron, 100 micron, 50 micron, at a given bias of VR, before avalanche occurs for that device, if the widths are such that at that reverse bias, whole N region gets depleted. What does depletion means? No free carriers. There is a strong electric field there. So any carrier entering from P side now, that is electrons, are picked up at the contact without any interaction with anyone. So large number of electrons can be picked up, large number of holes from contact can go to the P side, and you may see again larger current. Punch through means you have punched the base. You have punched the base, that is deplete the complete base. If you deplete the base, there is no recombination, all of them will, because of large, remember larger the depletion, the electric field here is very large. So you can see from something like this, this is an example of interest for anyone. If I have an inclined plane, this is larger slope, this is smaller slope. If I keep 4 electrons or 4 balls here, okay, and push them, irrespective of the slope, only 4 can reach to the ground level. Is that clear? So slope means equivalence of electric field. This is the potential diagram. If I show you, You say electric field larger or smaller, not much. How much available will only decide you will get. As many will come from you, all will be swept away. So larger currents can be seen as you start reverse biasing. Any number of carriers can be pushed out, and therefore you can get this value. Now this depends on what value then? Doping of course, but what essentially? The width of n region you make a choice. So you can remember what is our width formula? Twice Ks epsilon naught. Now since it is n type, Q n d into. Now if this W is actually Wn, one knows at what value of VR it will punch. Is that correct? If the depletion layer is exactly equal to the n region lengths or widths, then I know at what voltage for given ND this will reach to the contact. So I know that voltage at which this will occur. That voltage is called punch through voltage. What is it called? Punch through voltage. Most devices which you use are punch through devices. So how do you tailor that? The length of n region in the case of P plus N junction is actually tailored by designers. 5 micron, 10 micron, 50 micron, 100 microns, and doping is kept at 10 to the power 14 per cc. So I know at what voltage this will punch. So when you say 10 volt something is this, I can adjust my W so that at 10 volt itself it punches. 5 I can punch, 50 I can punch, 5000 I can punch. Is that clear to you? Now this means the Zener device which you keep saying at 3, 5 volt, 10 volt Zener mechanism will now see last, does not go beyond few volts. But now they are saying Zener of 5 volt, Zener of 10 volt. How can you have a Zener mechanism at such a large voltage? So which device is being used there? The punch through device with the base length so adjusted that it breaks down at the value of your choice. So most of the circuits which uses breakdown values known to them in priori, they use punch through device. Is that correct? So this is the second mechanism which, as I say, can occur because of P punch through any value. But if I see the third mechanism, less than 3 volt itself, the heavy current starts flowing. So there must be some more mechanism which of course will also reduce further the breakdown value. That mechanism is essentially related to this physics and slightly not very different from other physics, but let's look at the situation. If I have a barrier, potential barrier, something like this is theory. Okay. If you find empty states here and you find filled state here, sorry, yeah, this is empty. If this potential is reasonable enough and this width is very small. So what does that mean? If the width of the barrier is very small but the voltage is sufficient, then what is larger here? V by W is electric field. So if the electric field rises substantially more than 10 to the power 4, around E tends to 10 to the power 6 volt per centimeter. Now according to quantum mechanics, what does it say? If electron can occupy an empty state at the same energy if the electric field here, width here is very small. So an electron can directly go to the empty band and fill it, because probability says it can occupy even this side. Is that clear? This mechanism is called tunneling. This mechanism is called tunneling. Also, since it is field dependent, since the larger field allows this tunneling, it is also called field emission. So in PN junctions, can we get a situation in which, where are the field state in the PN junction? Valence band below are field state. Where will be the empty state possible? If the conduction band goes below the valence band of the other one. You got the point? You have a valence band here and you have a conduction band, the other side is lower. As soon as it sees this situation, these are all available state and these are all field state. And if the barrier width there is very thin, electrons from P region will jump to the N region, which is what normal all reverse biases have been doing, which means current can start flowing because of tunneling. There is one more possibility, in this case it may not be. This may not be small enough, this is a large enough. Let's say these electrons acquire some energy by applying voltage, but somewhere here it finds now thin enough barrier, so they may actually go and then tunnel and then fall down because of this. This is called thermionic field emission. But let us say these states are not available like this, barrier is also high, no tunneling or no thermionic field can do, but you still keep putting an energy which crosses this barrier energy, then also it can go from P to the N side. That when the electrons reach full barrier height and then drops is called thermionic emission. So which three methods of transport possible across a barrier? One going over the barrier, one climbing a bit, then tunneling, and one tunneling at the lowest of energies. Three mechanisms are possible. These are used in some other device. Just now I will talk about them now. So how do I get this status? Now let's look at the figure. और थोड़ा सा अच्छा शार्प कर देते हैं. This is p-type material, EFP. This is EVP, okay. And this is ECP. ECN, EVN, EFN. ये थोड़ा ज्यादा ही दिखाया मैंने, बट थोड़ा पास भी कर सकता था. ये कौन से इलेक्ट्रॉन्स हैं यहां तक? बाउंड इलेक्ट्रॉन्स हैं, बट अवेलेबल हैं. इस साइड क्या है? सब जगह फ्री स्पेस है, कोई भी इलेक्ट्रॉन ऑक्यूपाई कर सकते हैं. So there is a possibility, if this W is very small, electrons from the valence band can then go towards conduction band of N region. This is a distinct possibility. This is called tunneling. Now how it can occur? When you have P plus N plus junctions. If you have a P plus N plus junction, what is the built-in voltage, larger or smaller? If dopings are higher, KT by Q ln NAND by NI square. Larger the doping both sides, larger is the built-in voltage and larger is the built-in electric field. If you apply reverse bias, that means the Fermi potential in P is larger than Fermi potential, Fermi energy on the N side. That's a reverse bias. So if I apply V0 plus VR now, and if the dopings are very low, very large, what is the depletion width will be? Larger doping means depletion widths are smaller or larger? smaller the depletion widths, voltage gap is enough now, V by W will become larger electric field, may reach a voltage fields of 10 to the power 6 volt per centimeter, and if the bound state sees an empty state when the barrier width is very small, electrons from the bound state can actually tunnel into the empty state, creating what we call as Zener breakdown. Zener, of course this mechanism was not found by Zener, okay. He was actually doing from the metal emissions, but since the mechanism was like that, repression of the mechanism, so they say okay, honor Zener for this, okay. So this is Zener mechanism or tunneling mechanism which was observed, and since you don't large VR, why? Because P plus N plus itself has given enough V0 for you to create larger electric fields. So even with smaller VR, carriers can go from P to N and therefore current can start. Is that okay? Is that okay? So is tunneling clear why it is much lower voltage? Dopings are extremely high. We will not see it today, but maybe some other day. So reverse bias, yes, you have seen it like this, but the forward bias characteristics of this diode is very funny. It shows very interesting forward characteristics, PN junction, P plus N plus junction. What this region is called should be, I am increasing voltage, but I am decreasing current. So what is it called? Negative resistance. V proportionalize Ohm's law. Now it is found that V is increasing, I is decreasing. Such device can therefore, instead of dissipating, can generate. These are used for oscillators. Okay. So if I bias here, apply a signal, I will see larger on this. These are called tunnel diode oscillators. Okay. So negative resistance leads to oscillations. In contrast to the other case, it will damp down IR loss. Okay. Here it will actually generate the power out. Okay. Please remember, nothing can be generated. What is it doing? It convert DC into AC. No energy is created. It is only converted. So DC voltage will get converted into AC signals by negative resistance. That's why these are used as signal generators. Okay. Signal generator. You can see from here in this DC region only, if I increase signal corresponding to this, I will get larger AC signal because of the slope. If it is sharper, largest variation will be seen at the output. So larger signal. So the DC value only has allowed it to convert it to the AC value. No energy can be created is a thermodynamics. So kahin na kahin se to energy aana hai. Is that okay? So these three mechanisms of device, what we call as the reverse breakdown characteristics, are essentially related to three mechanisms. Which is the most dominant one? The punch through. Most devices will be punch through kind. Okay. So unless the breakdown is really 3 volt or lower, because at very low voltage getting a punch through means W will be so small I cannot make the device. Is that clear? Let's say W is required 0.455 micron, I cannot create that. So probably at very low voltage there will not be any punch through device. 5-10 volt yes, but less than 1 volt or 0.8 I cannot punch through. Before we quit, one interesting feature you must remember. All devices, at the end of device, this is a semiconductor. The external world wants contact of metal, because it should have low conductivity, a large conductivity, no voltage drop. Now the problem starts here. You have a metal and you have a semiconductor. Now we know two different materials, if you join, there will be an issue. What is the issue? If the word which I am now going to introduce, the metal work function is not same as work function of the semiconductor, then there will be something will happen, and will create a barrier. Okay. Now what is it? That's last part of this junction. So what is ideal ohmic contact? We say ohmic contact means what? Whatever carriers are coming here without getting modification goes to the external world. So essentially good ohmic contact should have ideally this characteristics. No voltage drop anywhere. But nothing can be done like this. Best of ohmic contact will be something like this. Okay. Very small drops, huge currents, very small drop, huge currents. So this is what in all the world we want to do, ohmic contact. So the junction should be so quick that it should allow all carriers to go across metal semiconductors, then only you can have a ohmic contact. If it creates a barrier, let's say because of something like this, then this will be same as like this. Is that clear? So my worries are how do I make a good contact? So let me first quickly look into a contact. Now this metal semiconductor contact theory was suggested by a very famous solid state man, and his name is Schottky, and the barrier it creates is Schottky barrier. Is that okay? This is a metal semiconductor contact. The theory is very, very interesting. Will not deal so much. So much so, the very topmost VLSI scientists in earlier times have their PhDs actually done on metal semiconductor contacts. Okay. Very, very top people who worked, became very famous in 70s for their research in VLSI design, actually where their PhD work, and one of them is me. Okay. This is a joke. Okay. Okay. Let us say, just look at it. Please, in the metals, what is metal essentially is defined by there is no conduction band, there is no valence band, and the Fermi level is pinned at the maximum, up below which electrons are available, above which no electrons are available. So this is my metal. There is a fictitious level which is called vacuum level. Now this is not really fictitious, but in a way there is a fictitiousness there. Why we want to use this word vacuum? Because let's say if I have a material and I start heating, let's take this metal, I start heating, okay. Not every material actually emits electrons, but certain materials do, okay. What does that mean? The energy required for an electron to go from metal into free state, not bound to the solid, is called work function, is called work function. The carrier's electrons to leave its parent crystal and go into free space is called work function. Now it is defined in vacuum because this emission can only take place at relatively lower temperatures if you have a vacuum there, okay. Evaporations of any material, let's say I want to deposit aluminum here, I take a tungsten coil, put aluminum rods inside that, thin rods, keep it in a vacuum chamber, okay, and heat 200 amps current, it will get reheated and that aluminum will melt and will start evaporating and it will deposit from the bottom. This is essentially called evaporation, okay. This is a simple theory. In vacuum it is done that the mean free path will be larger the mean path, all atoms will actually hit here, otherwise they will scatter, okay. So all the levels, all the materials are deposited at vacuum, So that energy we assume where it will come out is called the vacuum level. So arbitrary in that sense. This value is called metal work function. Is it clear? An electron to leave metal and go to the free space is called work function for. So every material has a work function. Is that clear? It's not just metal. Any material, you name one and we'll have this. Let us say I have a semiconductor like silicon whose work function then is defined from where to where? From the Fermi level in the semiconductor to the vacuum level. So let's put, okay, this dotted line somewhere here so that I know where I am, or maybe I'll put it here. Let's say this is my EC, EV, EI, and this is my EFS. What is this value? Instead of phi m, you call it Qy because it's energy term. So this is Q phi S. S means semiconductor. The energy from the conduction band, actually this is most important energy. What is it essentially? Already electrons are free here. Okay. And then they are leaving this. What is it called? It's called electron affinity. Q chi. Chi is taken from the conduction band above which electrons are anyway available to the vacuum to leave the metal is called electron affinity. This is the energy which is binding it to the crystal. Phi S is, now let us say these two materials I bring closer. There are two distinct materials, one has Fermi level here, one has Fermi level here. Okay. So what will happen if I bring this metal semiconductor joined together? What will it happen? Gautam, क्या होगा? सोचो ना, जब भी dissimilar materials we bring together, like in PN junction, what did we do? Fermi levels must get aligned. And how will they get aligned? Unless electrons from the semiconductor leave and join the metal side, only then this Fermi level will start aligning. So if I do that, I will now see something like this. इससे कोई and what is this? This is the barrier potential like V0 we did for PN junction. Well, how much is that? Can anyone suggest? And this, oh sorry, but how much is this? Okay, another term you should now know. Fermi level minus EI, EF minus EI. What is this actually? This, what is it called? Fermi potential. How far you are away from intrinsic is called Fermi potential or Fermi energy. So this is given a name phi F. Phi F is EF minus EI or EI minus EF is phi F. By Q of course, because EF by Q is voltage. So maybe you can write Q phi FF. So if you see this minus this, if you do this, then you get now this Q phi M minus chi is essentially this value and given a name phi B, barrier height. Phi B is called barrier height. Is that correct? What is the word used? From Fermi level to the top of the band is called barrier height. Now can you think, this is like a normal PN junction. Is that clear? It's a normal PN junction. If an electron has to go from here to here, how many ways it can go? Let's say electron goes from metal to semiconductor. How many ways it can go? Either it can go like this, or it can go like this, or it can go like this. So all three mechanisms are possible for electrons to go from metal to the semiconductors. Thermionic emission, which is thermionic emission? Going whole phi b, okay. Halfway it goes and then tunnels, then you say it's thermionically field assisted as we call it, or field itself is sufficient. When will be the field larger? When the width is small. When the width will be smaller? When the doping of semiconductor is very high, very high. Is that correct? So if you have a metal semiconductor with semiconductor heavily doped, most of the carriers can go like this. So which is the equivalent case here coming? Ohmic contact. So if a metal semiconductor contact to have a large tunneling current both forward and reverse, then you should have heavily doped semiconductor and metal connected to it. But if it is lightly doped, it will create a barrier, okay, and if it creates a barrier like a PN junction, it can have plus positive and forward bias, reverse bias currents. However, forward bias currents will be from, let's say I put positive, negative, where Fermi level will move in this case? If I apply forward bias, where will the Fermi level in metal and go with reference to semiconductor? Which one will be higher? Negative and negative energy plus energy, electron energy increases, so Fermi level in N will rise above Fermi level in metal. So if you want to do this, let's start looking like this. The barrier will become V0 minus Vf, okay. This is my Fermi level, this is my Fermi level in the metal. It can be anywhere, but this is the voltage. What is this voltage? This is QVF. Separation of the Fermi level is the applied voltage. Fermi level in semiconductor will go higher than in the metal. This is forward bias. In the reverse bias, what will happen? The Fermi level in the semiconductor will be lower than then this voltage is Q and this will become V0 plus. It's like a PN junction, so rest of the transport is similar, and therefore the only thing, because it is proportional to this, maybe I don't want to derive this, but just look at this, A star T square e to the power Q phi b by kT into the power EQV by kT minus 1. What is A star is called? It's called Richardson's constant. Okay, A star is called Richardson's constant. This relationship is used in Schottky barriers, plus or minus. Is that correct? Minus taken where? V becomes minus is same opposite current. V taken plus means the other side current, okay. So this is like a diode. So a Schottky barrier acts like a diode. Is that clear? Schottky barrier acts like a diode, and if it is heavily doped, it acts like a Zener diode on both directions, okay, and shows ohmic contacts, okay. This is how. So is that clear why I actually use this? I am going to go to a MOS capacitor now, and now that's what, please look at it what I am now going to do. Schottky barrier has metal semiconductor. I am going to introduce between semiconductor and metal an insulating layer, okay, an insulating layer. So what is its name now? Metal oxide, because silicon dioxide is an insulator. Metal oxide semiconductor, MOS, the word which all world is now talking about MOS technology, comes from this fact, metal oxide semiconductor. Now this insulator creates problem different from Schottky barrier. In Schottky barrier, what has happened, as soon as I touch metal, electrons went and Fermi level aligned. Now there is another material in between whose Fermi level also I don't know because it's an insulator. Why I say I don't know Fermi level in insulator? Because the band gap is so large, it's only fictitiously large, and 8 electron volt, 9 electron volt, and where is its position from the vacuum level? So depending on that, if all 3 Fermi levels have to align, what things will happen, whether the carriers can go from metal to semiconductor at all will be seen. But one thing very clear, simply looking, since it's an insulator, equivalent to saying R tends to infinite, there is no DC current possible in MOS. Typically, it's not that it doesn't leak, but it leaks practically negligible. So what is the difference between MS contact and MOS? MS transport occurs. Carriers go from metal to semiconductor, semiconductor to metal. In the case of MOS, there is no transport from metal to the semiconductor or semiconductor to the metal. So what does it look then? इसको थोड़ा सा vertical कर दें. This is my semiconductor. This is my insulator. This is my metal contact on both sides. क्या दिखता है आपको? अच्छा चलो दूसरा फिगर और बना देते हैं. ये मेटल प्लेट है, ये मेटल प्लेट है, ओके, एंड ये इंसुलेटर है बीच में. व्हाट इज इट कॉल्ड? कैपेसिटर. इज दैट क्लियर? So a metal insulator metal is a capacitor. Is that clear? So MOS also must behave like a capacitor. Okay. But what is the difference? Before we actually work tomorrow, the major difference which I see in MOS and a normal capacitor. Let's say I take this capacitor in a circuit. AC current can pass through this way or pass through this way, and if I given frequency, let's say this is C, this is the impedance seen by the capacitor. Is that clear? Direction is irrelevant. Is that correct? So if I monitor voltage versus capacitance for this, whether it is positive or negative, the capacitance is monitored same value. But if I do the same measurement for this system, which is metal, this is metal, this is also bottom contact metal, and this is an insulator SiO2, then I find something interesting. Let us say if this material was P-type semiconductor, I figure out if I apply reverse bias or minus voltage, capacitance is such large value constant. But if that means this is negative, means this is negative, this is positive. Okay. Metal top plate is negative and bottom, that is oxide, the other side is negative and P is positive. If I apply opposite polarity, then I find, maybe slightly here, the capacitance starts decreasing, and at certain value which will define that, depends on the measurement frequency, may become constant, or if the frequency, this is called high frequency CV, and a low frequency CV, it goes back. This value will define as oxide capacitance, and there is a minima observed on the forward positive value. This value at which the minimum value is reached is called threshold voltage of the capacitor. Threshold voltage of the capacitor, at which the capacitance becomes minimum. Capacitance become minimum. Either it may remain constant whether the measurement frequency is higher, 1 megahertz and above, or if it is very low, 1 hertz to 10 hertz, it may climb back to its Yox value. Now this CV is different from this CV. Is that clear? If I have a normal capacitor as you show here, I see a constant capacitance whether I put plus here or minus here, it's fixed. You put the ceramic capacitor, you don't look for polarity. You just put whichever way you put and it doesn't give you any difference. In the MOS capacitor, there is a difference, okay, which means there must be some mechanisms going on to make this, and this fact is what makes MOS circuit or MOS device very interesting. Before we quit this, let's say in a normal capacitance, if I apply voltage V, what does that mean in a capacitor if I apply positive voltage V on this plate? What does it receive in charge? Positive charges. So you find positive charges. But now our great person called Gauss, he said around a loop the net charge has to be like a Kirchhoff law equivalence, or rather Gauss's law's equivalent was a Kirchhoff law. The charge along a loop is constant. So on this lower plate, let's say this was Q1, so he says Q1 plus Q2 must be equal to, assuming there are no charges in this. Is that correct? If that happens, then Q1 plus Q2 equal to 0, and if Q1 is positive, Q2 is minus charge. What is this word we used earlier, 7 to 10 standard? Induction. Positive charge will induce negative charges on the other bottom plate. Is that clear? The same mechanism will now occur here. Okay. Which law I am going to use often? The Gauss's law, which is one of the 4 electromagnetic equations, Maxwell's equation, which states Gauss's law, the net charge around the loop is or surface is 0. Okay. This law, what we learned 7, so abhi second year में भी वही master करोगे तो भी वही PhD करोगे तो भी, तो ये law बदलता नहीं. इलेक्ट्रिकल में 2-3 law ही यूज होते रहते, एक Gauss's law, एक Kirchhoff law, and third maybe if magnetic fields are used related to magnetic field laws. बाकी तो कुछ है ही नहीं, हमको इतना ही आता है, बाकी तो कुछ आता नहीं ना. तो हम इसी के ऊपर let's see how in a MOS capacitor it gives me very typical characteristics as shown there, where a normal capacitor. So what is the direction of electric field if it is positive here, negative here? Yes, which is the direction of electric field? Always field lines start from where? Positive terminal and end on negative terminals. Each positive must get equivalent negative charge here, so that all field lines terminate from positive charge to the negative charge. That's how the field method sees. Right now my assumption before we quit, which is what we say, these are 2 different materials, metal, semiconductor oxide and semiconductor. The Gauss's law say or may not say, but we say one of the Gauss's law says D is continuous, electric vector is continuous, D is continuous from here to here. This is what makes us very interesting. We'll then evaluate, what is our interest is, I am more interested in this value, how much is the threshold voltage, because in transistor this value tells below which current is not there and above which current is available to me. Is that clear? So I am very keen to know what is this Vt value. Okay. Once I know Vt value in a transistor, MOS transistor, I will be able to get currents. Once I know my currents, I know everything in a circuit. Okay, and that's what I am interested in. So see you tomorrow again at 11:30.